Hi, my name is Aaron Lahoy, and I'm a computer engineering major at Grand Valley State University. I'm the team captain for the DornerWorks Accelerated AI Vision Networking project, and our objective for this project was to create an interactive demonstration for DornerWorks to use in a convention setting that exhibits the functionality of their time-sensitive network switch using a live video AI system.
Hi, I'm Nolan Smith, and I'm a computer engineering student at GVSU. The complete setup of the project uses a camera to capture input video, intermediary components to process and handle the data, and a display monitor to show the final product. I'll now give a summary of each component as it works in the system.
The project prompts users to play a game of rock, paper, scissors against each other in front of this camera here, which is then fed to an NVIDIA GPU, which specializes in AI performance. A program running the trained AI model on the GPU then evaluates and assigns values to the incoming frame based on the two users' hand gestures. That data is sent through the TSN, prioritized, and forwarded to this Raspberry Pi, a small computer capable of overlaying a user interface on the final sets of data and sending the complete interface to the monitor.
Hi, I'm Jaden Roloffs, and I'm a computer engineering major at GVSU. The TSN was developed by DornerWorks so important data packets aren't lost as a result of a network attack. The TSN does this by assigning priority to the more vital data in the system. In the scenario for this demo, we have two sets of data moving through the system, the live video stream data and the AI metadata interpreted from the rock, paper, scissors game. We considered the AI metadata to be more important than the video so games can be played even when the network is under attack. The red button and the Raspberry Pi are connected directly to the TSN and simulates what would occur during an actual network attack when the button is pressed, a flooding of the network with traffic, and an effort to render the system unusable. However, the TSN is able to prevent complete system breakdown and still lets the AI metadata through. As a result of this, during an attack, the display interface will show a blank background but still retain the bounding boxes from the AI data of the rock, paper, scissors game.
DornerWorks having developed the TSN and Jammer, it was left to us to program the GPU and the Raspberry Pi for the display monitor. The two devices were coded with Python utilizing many different libraries such as OpenCV and GStreamer. Many software network and debugging tools were used to confirm packets were being transferred from the correct location with correct tagging. TCP dump was useful in determining the priority and status of incoming data.
Hi, I'm Paul Durant, and I'm a computer engineering major at GVSU. One of the main issues dealt during development had to do with system latency. DornerWorks requested a delay between camera capture and display be less than 250 milliseconds, or a quarter of a second. The first iterations of the system went way over this, prompting us to make some changes to the system. Encoding the data in a different format had a slight positive impact, as well as multi-threading the render code for the display. The main improvement came from upgrading the Raspberry Pi we're using as a display model to a more recent model with a higher clock on the CPU. The initial model we were using couldn't keep up with the speed of incoming data, causing lag on the output screen and hence the majority of the latency.
This is a demonstration of a couple of rounds of rock, paper, scissors with two players. The game sequence begins once one person is detected on both sides of the play area. The first round results in a tie, prompting the game sequence to restart and have the users play again. This time player 2 wins, making their score go up by 1 and stops the game from initiating another round until more people are detected. Notice in this round that the user pulls their hand out of the way before a result is shown at the top. This logic was implemented purposely to prevent any false detections that may occur in split seconds between a user switching hand gestures. Now we show what the game looks like when the jammer is active. After pressing the red button, the jammer floods the system, causing the video to completely freeze since no data is reaching the Raspberry Pi display. However, the TSN keeps the AI data intact, which can be seen by the bounding boxes still following the user's hand movements.